We are going to be talking about the routing problem for a vehicle in logistics, and we're going to be starting with the classic traveling salesman problem, where we're basically determining for a set of customer locations a route that minimizes typically the distance traveled to visit all of the customer locations and then returns back to its starting point. And we're going to be talking about a series of different ways of actually constructing solutions and improving solutions to the TSP problem. In terms of the sets of functions that are available for the TSP problem, and then also for the related vehicle routing problem, if you look in the help information, there's a whole set of problems that are developed that are specifically for these two problems, and these will be the procedures that we'll be talking about today in this video. And they're a set of really classic problems. They're characterized by, in the case of the TSP problem, of being the classic TSP problem, and then in the case of the VRP problem as being problems that have a single depot. And then later on, we're going to be talking about a more general set of routing problems that allow us to have multi-stop routing problems and to have each customer and each shipment have a different origin and a different destination. So this is a much more general formulation of the routing problem that'll be covered in our later scripts and videos. But for today, we're going to focus on the classic TSP problem. And these are the set of functions within MATLAB that have that data. And then the other thing we'll be using is, when we get down to the bottom, there's a set of data. And in particular, for today's video, we'll be using the VRP NC1 data set. This is a classic problem instance, both for the VRP problem, and then we can use the same data, and it's also a classic TSP problem instance. So we'll be using that as our set of data for this problem. That particular instance, it's from a paper by Christophilus, and was basically he had taken a TSP data set from the TSP library, and for that problem we know what the optimal solution is, 426, and that instance is called EIL51. His co-author was last name Elon, E-I-L-O-N, so this is called the Elon 51 problem. It has a total of 51 data points, and for the VRP problem, the first data point is the depot, and that's the starting point, and then there's 50 customers. For our purposes, for the TSP problem, we'll view it as having a total of 51 customers. And then the data that we'll be utilizing are the XY locations of the customers, and then Q, which will represent the demands of each customer. And then it becomes a VRP problem when we add things like a maximum load ability for the vehicle. But for the TSP problem, we're assuming that there's no constraints on how much the vehicle can actually carry and cover. So to actually load all of the data for this problem, just execute the name of the function. So just like with the US city data, the name of the function allows us to look at the help information plus actually get the data, which is in a .mat file. And then if we look at the workspace, in addition to the two things that we need for the TSP problem, which are the XY, the 51 by 2 matrix of XY locations, and these are Euclidean distances, so they're not longitude, latitude, they're just Euclidean distances. And then we have a vector of demands. The other information, Q, capital Q, represents the maximum vehicle capacity, and we also can put constraints on the maximum total cost of a route, and also LD represents the time for loading and unloading. All of this data can be utilized when we are solving the VRP problem, which we'll be doing at a later time. But for now, we just need the XY and the Q variables. So the first thing we can do is, since we've downloaded the XY locations, we can call pplot, and it then indicates the set of locations for all our data points. And then the first procedure that we'll be talking about is the space filling curve procedure for the TSP problem, developed by John Bartholdi from Georgia Tech. And the help information, in terms of the things that are input for this procedure, we basically just have to give it the XY coordinates. There is a second input parameter, K, and it's the number of binary digits to use. And we're almost always going to be using the default value of 8 binary digits. That gives us more than enough accuracy for any problem that we're interested in. So almost always we just ignore the second optional parameter. So we can call it just with a single parameter and not supply a second input parameter. And what we get then as a result is a location vector. And that is a vector of n plus 1. So if n, in our case, n is 51, we'll get a total of 52 values returned. And the last value returned will be a repeat of the first value. And the reason is that this route returns back to its origin. So there's no gap. It basically connects all of the points and then returns back to the starting point. And for this problem, there's an example showing its use, which is basically the same thing. That is what we'll be doing in this script. So for the data points, originally we plotted them just as red points. To be able to number them, we can execute pplot, where we actually convert the numbers 1 through 52 from numbers into cells, which can then be used to label the points displayed. So this is, well, we know exactly what points are being referred to. And then to actually solve the problem, we just give the XY as the input parameters. And here we get a total result of 52 with the 1 being returned. And to actually then plot that, one way of using pplot is we can give it as a first input argument a cell array, where the cell array includes a route. In this case, it's a location sequence. And that location sequence will then be plotted. So this then shows in green the overall sequence. Since these are Euclidean distance symmetric TSP problems, when evaluating the solution and looking at it, you can immediately see that one thing to be on the lookout for is any of these arcs that are crossing. If we see arcs crossing with a symmetric Euclidean distance TSP problem, we know immediately that that can't be the optimal solution, that if we can get rid of the crossing, we can improve the quality of the solution. And in this case, for this TSP problem, we see that we don't see any crossing. So at least from that point of view, it looks like a good solution. So at this point, what's interesting is that for the space filling curve problem, we don't need to create a cost matrix. The space filling curve just utilizes the XY locations, but to be able to determine what is the overall cost, and our cost will be the total Euclidean distance required to travel, we'll need to actually calculate that distance. So at this case, we need to actually create a C matrix. So we'll use the distance function with the type of distance being a 2 because we want Euclidean distance. So this has created a 51 by 51 matrix of distances between all of our points. And then we can utilize the function in MATLAB called loccost. And what that does is it allows us to calculate the cost of a location sequence for all the different pairs of locations. And what it's doing then is when we actually call it, for this problem, it's giving us a result C, lowercase c vector that has 51 elements. And it's basically telling us the element distances between each pair of points. So these are the Euclidean distances. For example, if we look at our location sequence, it starts off with location 1, and then we travel to location 7. So what is the distance going from 1 to 7? In our C matrix, that distance is 11.4018. And if we look at what's returned by the location cost, that's the same 11.4018. What it's actually doing, we can use the type command to see what is the actually code that's inside of the location cost function. And the code is actually just one line of MATLAB. And it's just a way of kind of hiding the fact that we're going to be taking the C matrix and going from the first location point to one less than the end. And that gives us then all of the starting, the row coordinates of the C matrix. And then to get the column coordinates, we take the second element in the location sequence all the way to the end. That gives us our column indices. And then we're rearranging the elements in the C matrix. And then it puts our desired output along the main diagonal of the resulting rearranged C matrix. And that we can then assign to the C vector, which is exactly what we want. So to do this, you'd have to understand a lot about what MATLAB does. This is an example, I think, that's talked about in the basic concepts of MATLAB that we studied earlier in the semester. And since conceptually it's kind of hard to remember all the details, what the location cost function does is just collapse that into something that from a use point of view is more straightforward, where when we call location cost, we just give it the location sequence and the resulting matrix and don't worry about exactly how to create this rearrangement and then taking the diagonal. So this is just a way of sort of chunking the data so that it's more useful. And then since we had the individual cost elements between each segment of our resulting location sequence, and I use the term location sequence and not use the term route, which you would think would be more appropriate. And the reason is that later on, when we have multi-stop routes with different origin destinations, we'll be distinguishing between a route and a location sequence, and they're not the same thing. So I'll try to remember to use location sequence instead of route when we're talking about the TSP problem, so that we're consistent in our later discussions. And we then, instead of wanting the individual elements, we typically want to look at what's the sum of all of those together. And for this problem, then, the sum of all of those together is 482.7. So this is the quality of the solution. And for this particular instance, we know actually, since it's a small problem, it's been solved to optimality. We know that the optimal solution is 426. So we're actually quite a bit of ways from what the optimal solution is. But given the simplicity of actually solving the space filling curve and also its computational efficiency, it actually works fairly reasonable to give us a pretty good solution. But we can potentially look at trying to actually improve from that. And here again is the help information for the space filling curve. And if we want to do everything in one step, we can take our resulting optimal location sequence, and instead of having to first call location cost to get this cost vector and then sum up all of those elements, we can do all of that in, again, one function call. That function call is location total cost. And in that case, we just give it the location vector, and we could pass it the C matrix, but instead of actually having to create the C matrix, we can just give it the code that would create the matrix as the second argument. So this allows us to just in one step get that total distance. And then the reason for these functions are, since we need to do this quite frequently, we don't want to have to do all this intermediate detailed work if we're really just interested in what is the total distance given a location sequence and the distances between the different locations. Then with that information, location total cost can determine that total distance. Then with that solution, we can also consider executing different improvement procedures, and the only one that we'll be illustrating is the 2-opt edge exchange or arc exchange procedure. That's also part of MATLAB. This is the information for this, and as you can see, there's a lot of different input arguments that are possible for this. And in our case, we just really want to use the location sequence and the cost information, which in this problem is the distance between the different customers. These three input arguments are input arguments that are used for the VRP problem, where we have capacity constraints and time windows. and other types of input information that we're not going to be talking about today. But there's a last output argument, which is h, which is the handle that was returned by the p-plot. And the reason I'm going to be specifying this as an input to the TSP problem is when I do that, then the procedure actually calls p-plot as it's making changes to the route, and you can then visually see dynamically what are the changes occurring as the code executes. So if you just want to get the solution and then do an improvement, you could just specify these first two input arguments, and if you don't want to actually see the plotting occur. So really this is just for demonstration purposes that we're specifying this sixth input argument. Otherwise you would just have two input arguments. And then here, before actually starting to run it, the figure actually says press any key to continue. So it waits till you're ready to see it. And you can also, if you look under the MATLOG menu, you can specify what the pause plot time is. So if you find this executing too fast on your computer, then you can actually put a delay so you can see each step as it's occurring. And you can say it just made a couple changes, and it reduced it from the original 482.7 down to 456.27. So it gave us a nice little reduction. You could see visually what the few changes were made in terms of doing edge exchanges. Another thing is if you look at the slide talking about 2-op improvement, it basically gave an example for a 6-node or n equals 6 example, and then it showed what are the different edge exchanges, and for that there are a total of 9 different edge exchanges. Well, exactly how does that number of edge exchanges, how is that determined? And more importantly, that type of edge exchange procedure is a n-square procedure. So as we increase the number of customers n in a solution, the cost of doing a 2-opt improvement goes up as the square of the number of nodes. And that's important information to know in terms of computational efficiency. If our improvement procedure was n to the 3, n to the 4, that would be very, very time consuming. N squared is on the order of being sometimes reasonable, but even that, even an n-square procedure can be somewhat time consuming if we have very complex problems. So I'd like to spend just a few minutes to kind of talk about how we would actually determine the result given at the bottom of that slide, showing that the overall result is n times n minus 3 over 2, which for n equal 6 is equal to 9. How is that actually determined? And the way that you can do it for, and essentially if you look at the figure, you can see that there is illustrated the 9 different possible edge exchanges, and other ones are not possible because it's not feasible to exchange any edges that are incident to the same node. So you basically, for A, it can only interchange starting with C, D, E, and then it can't interchange with F. So for the A procedure, its interchanges are, the total number of those are specified here. In this case, for n equal 6, there are a total of 4 edge exchanges. And then for the remaining edge exchanges, starting with B, they can make exchanges with, in B's case, D all the way through F. So all of the other ones can go all the way up to the last arc F, and A is the only one that can't do that. That's why these two terms are separated. So starting for arc number B up to, the last one considered was D. So there's no exchange of E because E is adjacent to F, and E and A have already been accounted for here for A. So that's why everything stops with D. So here I goes from 2 to n minus 2, and then we do that for starting with not the next arc, but 2 arcs away. So that's the reason for the form of the equation given. But how would you actually determine that? One way to do that is to first start off set n equal to 6, and then for the first arc A, the 2-op procedure is basically generating these interchanges. So I'm just duplicating what's shown on the slide. These are the sets of, and instead of using A, B, I've actually used 1 for A, 2 for B. And I'm just listing what are the different edge exchanges that are occurring for A. And then starting for arc B, These are the sets, so in total there's a total of 9 of those. To look at it symbolically, we can do a similar thing, and MATLAB has a symbolic toolbox. And with a symbolic toolbox, instead of using the I, J, and N as numeric values, we can specify them to be symbolic variables by using the SYMS command, and that then turns them into symbolic variables. And if you look, you can see that in the workspace they've changed. And if you look at, for example, N, this is a symbol now as opposed to a double typical number. So this is now a symbolic variable. And then we can use a function called symbolic summation. And it gives us the what we're summing. In this case, it's just the number 1 that appears in the equation. And then it's starting from j equal 3 up to n minus 1. So this is how you translate the summation into a symbolic summation. So that's executed for the A arc, and then for B all the way to n minus 2, those arcs are executing the second call, and this is a double summation. So we have the inner summation to here, and then we have the outer summation specified to here. And then when we do all of that, it's going to create a representation of that, but then we're going to try to simplify it so we can get the overall simplest result. And there's a function in the symbolic toolbox of MATLAB called simplify. And then finally, to be able to see it easily displayed at the command window, there's a command to make it pretty so it's easier to actually visualize. So the result of all of that is that it goes through the whole work and it realizes that those two summation terms reduce to n times n minus 3 over 2. This is a capability in MATLAB I use quite a bit. If you have Maple on your computer system, then the MATLAB symbolic toolbox, instead of using its own built-in symbolic toolbox, which is based on an open source symbolic algebra package, which is, in my opinion, not really nearly as good as Maple. It uses that by default, but if you have Maple on your computer, then you can set it up so that the symbolic toolbox used is the Maple toolbox. So in my case, I do have Maple installed on my computer, so I'm actually running the Maple symbolic language whenever I do symbolic operations within MATLAB. Okay, next I'm going to be talking about another approach different than the space filling curve, and it's an approach where I'm going to start off, and I think the easiest way to explain this approach, first let me give the help information for this procedure, and what you want to concentrate on is what information is needed. In this case, all I need are the XY coordinates. So this tells me that for this kind of procedure, it's really only appropriate for Euclidean problems where we have the locations of the points. There are other problems that work even if we don't have the locations of the points. If we just have the cost matrix, then it's enough to operate just on the matrix. And that would be appropriate if we want to solve a TSP problem that does not have a geometric or geographic aspect to it. But for this convex hull insert, we're actually utilizing in the procedure the location information. But the good thing is that that's all it's required to solve it, so we don't need to specify the cost information. So in that sense, the convex hull procedure is similar to the space filling curve. So first I'm going to call up my set of points, and here's the final solution from the previous. And then when I call this procedure, the way it works is you could see it operating there. And in this case, I think it was really too fast. It was really hard to see what's happening. So I'm going to go ahead and go to the set. Instead of using 0 pause, I'm going to set it equal to 0.5, so a half a second. So I'm going to slow it down a little bit. So let me resolve it. And now it's a little easier. What's happening is it starts off with the convex hull solution, but then it looks at all of the adjacent vertices that are on the triangles that are along the adjacent hull, and it looks at which one can be added that gives us the least increase in total cost. And then it keeps doing that until it's complete. Another term for this procedure that's been suggested is the vacuum bag heuristic. Because you can think of it as starting off with a large bag, and then whatever the contents are, you're sucking the air out of the bag. So the bag then starts to encompass whatever the contents are in a very tight manner. And that's essentially what's happening here. Just like with the space filling curve, there's no crossing arcs, so there's not that improvement to make. What is the overall result? The space filling insert procedure, only, just like the space filling curve, only gives us the location information. So to determine what is the overall distance, we can use the location total cost function that we had talked about previously to see that we get a total result of 452, which is actually lower than the space filling curve with improvement of 456. And then we can do like we did for space filling. We can take this result and see if we can actually improve further from that. And this result was not able to do any further improvement. Another procedure is called the nearest neighbor algorithm. And the nearest neighbor algorithm, again, I'm going to go ahead and delete the figure, and we can recreate the figure. And before doing that, we can look at the help information. And here in particular, looking at what are we actually providing as input. So unlike the two other procedures, the nearest neighbor requires us to specify the C matrix. This actually gives us more flexibility because, as mentioned, it doesn't have to correspond to a geographic set of data. These could be data from a scheduling problem, and with that we can get a TSP solution. Second input argument is to specify what initial vertex do we want to start the nearest neighbor procedure, and we'll get different results as we pick different starting procedures. And then the third is the handle if we want to plot the results and see what's happening. So if by default we specify just a single C matrix with no initial vertices specified, in that case it looks at all possible vertices as starting points. So it tries every different vertex or customer as a starting point for the procedure, and then it only keeps and reports out what was the best overall result. So in terms of output, in addition to specifying the location sequence and the resulting best total cost, it also tells us which vertex did we start at that gave us the best result. An example of it, then let me go ahead and plot the same set of data, label it, and then at this point we can start executing the nearest neighbor, and it gave us this result. And this is a case where, in looking at this result, we can see that we have quite a lot of the arcs that are crossing. So there looks like there's quite a bit of room for improvement. What's typical of a nearest neighbor procedure is that it starts off and initially it makes good improvement, and it's selecting as a next vertex to add to the procedure ones that are very close. So this is sort of probably the sequence that this route was created. And you can see it does actually really well up until it gets to a point, and then the only time it starts to really have problems is when it gets to this point. All of the adjacent vertices have already been included in the route, so the next closest one is way over here at 0.44. So that's added, but then just like previously, there's nowhere nearby that's not already in a route. So 44, then its next closest is way over here at 41. And then 41 is not close to anything, and the only unlabeled arc is really to get back to the origin starting at 1. So everything up until the last 3 arcs, things were going really well, but those last 3 edges or arcs added to the sequence really increased the cost of the sequence. So this is not likely to have a good overall cost. So instead of picking 1 as my starting point, I can specify just an empty second argument and let it try all possible starting points. And now you can see that this is its trying of all possible ones, and the best one it found had a overall cost of 505, which is actually worse than all of the others, but we can try doing improvement on that. And with improvement, even though it started off at 505, which was higher than any of our previous results, after improvement, we ended up with 439. So we got actually a better improved result. So its nearest neighbor so far with improvement has been our best result. And then for our last procedure is a situation where we're really not going to do any type of intelligent construction. Instead, we're just going to randomly create an instance. And it's easy for the TSP problem because any random permutation of the customers is a feasible route to start with. This is not typically feasible for the VRP problem because a random route is likely to violate the vehicle capacity constraints or any other type of constraint. So it's unlikely that a random constructed route is going to be feasible for the VRP problem. But for TSP, we pretty much are taking advantage of the fact that it's always going to be feasible. And then the question is, if we just do improvement, how can we do just with a random starting point? So for this one, we're just going to be using the 2-up procedure. Go ahead and delete the figure, plot a new one. Then I'm going to set my random number seed to 100. And then to create my route, I'm just going to do call a function random permutation. And that random permutation is going to give me a random permutation of, the only input to it in this case is the size of the number of rows in the XY matrix. And that would be 51. But I'm going to set it so I want my starting and ending points to be 1. So I'm going to subtract 1 from the 51. So it's going to give me a random permutation of 1 to 50. But 1 I'm already using as the starting and ending point. So I just want it to go from 2 up to 51, or 52 instead of 51. So I can just take the random permutation and add 1 to that. So that'll give me a random permutation of the numbers from 2 up to 51. And then I can put 1 and 1 at the beginning and end of the resulting location sequence. And when I do that, I get this randomly created initial instance. If I look at what is the total distance of that, it's over 1,000. So it's double the worst solution I've gotten with any of the construction procedures that I've looked at previously. But from this really bad starting point, can I take that location sequence and then just by using the 2-op procedure, improve upon it? And you can see it starts off with quite a mess, but very quickly the 2-op improvement procedure is able to get the result down to 450, which is actually my second best procedure so far, next to nearest neighbor. If I take another random starting point, so I'm calling random permutation again, and I haven't reset the seed, so I'm getting the next available random starting point. So if you execute this code, as long as you do this first and then this is your second call to random permutation, you'll get the same answer I get. If you do it in a different sequence, then you'll get a different solution. So I can run that again. Here it got to 456, which is a little bit higher as a second run. And I can basically continue and just keep rerunning this. If I just highlight the construction procedure, the random construction procedure, and then the improvement, and I'm going to hit F9 again. So I'm running it a third time. I got down to the 450 result again. If I go back here, do it a fourth time, I got to 467, so this is actually my worst results, so on. And I could keep doing this probably for, do thousands and thousands, and if I get really lucky, I might get down to 426, the optimal. But I think for this problem, the 2-op procedure is not able to actually reach that optimal unless I just got really lucky with a random permutation. So this would be almost like doing the monkeys at a keyboard, generating a play of Shakespeare. It would take me, almost till infinity to actually randomly generate that. So I'd have to, not infinity, but 50 factorial is pretty close to infinity. So I'm not probably likely to really be able to achieve the 426. Question then is, how do you actually get the 426? And the way it's done is by doing a math programming formulation of the TSP problem, where you have cycle constraints that are added by doing column generation techniques. So it's a fairly complicated type of math programming, but when you get the solution to the math program, you have the optimal solution as long as the procedure stops and is able to actually evaluate the solution. So for this problem, they could actually solve and got 426 as the guaranteed optimal solution for this problem.